Hello everyone. In this video, I will solve the ordinary differential equation problems which are asked in 2011 June CSIR NET exam. Okay, and in this series, we complete all the questions which are asked in CSIR NET exam. It may take some time, but we will complete this series. Okay, so this is our first video of this series, and today's video is 2011 June CSIR NET exam, and the problems are from ordinary differential equation. Okay, so let's start today's video. Here is the first problem. Question number 41. This question is from part B, that means 3 marks, and only one option will be correct, and there is a negative marking. The question is, let P be a polynomial of degree n with n greater than equals to 2. So P is a polynomial and whose degree is greater than equals to 2. Okay. Then the initial value problem u dash t equals to p ut equals to p ut. Okay. And the condition is u0 is equals to 1. Has always option A unique solution, option B n number of distinct solutions in R, no solution in any interval containing 0 for some p, and option D a unique solution in an interval containing 0. Now for this problem, you can solve this problem by taking an example, or if you choose a polynomial of degree 2, then you can easily discard the incorrect options. But right now, I will solve this problem by using the uniqueness theorem. Before that, let me tell you what is Lipschitz condition. Suppose f is a function, f of xy. This is a continuous function. This is a continuous function. Okay. And if del f del y exists and is continuous in some domain D, if this exists and continuous, then this f satisfy the Lipschitz condition. This f will satisfy Lipschitz condition in D with respect to y. Okay. Now, what is uniqueness theorem? Uniqueness theorem is that if we have an initial value problem, suppose dy dx equals to f of x and y x0, this is our condition, is equals to y0. Now here this fx is a continuous function. This fx is a continuous function. Okay. If fx satisfy Lipschitz condition, then this problem has a unique solution. This problem has a unique solution. Otherwise, it has infinitely many or no solutions. Okay. So here this fx is continuous, and if this fx is continuous, then this will satisfy if this fx satisfy the Lipschitz condition, then it has a unique solution. Otherwise, it will have infinitely many or no solutions. Right? Here PUT in our given problem, this is our given problem. Here PUT, P is a polynomial of degree greater than equals to 2. And we know that polynomial is continuous, and dp du, this is also continuous. So this is satisfying the Lipschitz condition. Okay, that's why this problem will have a unique solutions, right? So in option D, you can see a unique solution in an interval containing the 0. So our initial condition is u0 is equals to 1. That means it is containing the initial point 0. Okay, so a unique solution in an interval containing 0. This will be the correct options. Okay, if you have any doubt, then you may comment in our comment sections also. Going to the next problem, question number 42. Consider the ODE u double dash t plus pt u dash t plus qt ut is equals to rt, and t is from closed interval 0, 1. There exists a continuous function P, Q, and R. There exist continuous functions P, Q, and R defined on this interval close to interval 0, 1. And two solutions U1 and U2 of the ODE is such that Wronskian W of U1, U2 is. Okay. Let me tell you, Wronskian, this will be either always 0, you may say it either always 0 or never 0. Never 0. Okay, so Wronskian, that will be always either 0 or never 0. Now check the options. In option A, WT is equals to 2t minus 1. And here WT is 0 when t is equals to half. So when t is equals to half, WT is 0. But in other points, in closed interval 0, 1, it is non-zero. So option A is incorrect. Either this will be always 0 or never 0, right? WT is equals to sine 2 pi t. Now, in this case, if t is equals to suppose 0, and because sine 0 is equals to 0, if t is equals to half and t is equals to 1. So if t is equals to 0, sine 0 equals to 0, t is equals to half, then sine pi is equals to 0, and t is equals to 1, then sine 2 pi, this is again 0. So in option B, Wronskian is 0, only these 3 points. But in all other points, this is non-zero. Okay, so option B is incorrect. Now check option C. Option C, cos 2 pi t. In this case, if t is equals to, if we put t is equals to 1 by 4, so this is cos pi by 2, and cos pi by 2 is equals to 0. So in this interval, closed interval 0, 1, only at the point t is equals to 1 by 4, Wronskian is 0. But all other points, it is non-zero. Okay, so option C is also incorrect. This is WT is equals to 1. That means here Wronskian is a fixed value 1, that is constant. And this is always non-zero. So in closed interval 0, 1, Wronskian is always non-zero. That means it is satisfying the condition of Wronskian that either always 0 or never 0. So option D, that will be the correct options. Okay, next problem. Question number 91. This problem is from part C. So that means it is containing 4.75 marks. And one or more options can be true. This problem is from Green's function. The Green's function gxj, and the interval is 0 is less than equals to x and j is less than equals to 1. This is zeta, gx zeta. Of the boundary value problem, y double dash plus lambda y is equals to 0. And the conditions are y0 is equals to 0 and y1 is equals to 0. Is option A, symmetric in x and zeta. Option B, continuous at x is equals to zeta. And these two options are given. Before solving this problem, let me show you some properties of Green's function. Here is the some properties. Number one is Green's function is always symmetric. That means here we have used gx zeta. Okay, so gx zeta and g zeta x, that will be symmetric. Number two, Green's function satisfy the given equation. Here it is our given equation, y double dash plus lambda y is equals to 0. So Green's function that will satisfy the given equation. Number three, gxt is continuous and has derivative up to n minus 2 order. It will have derivative up to n minus 2 order if the equation is of nth order, right? Number four, n minus 1th derivative has a discontinuity of first kind. N minus 1th derivative will have a discontinuity at x is equals to t, and the discontinuity will be of first kind. That means del n minus 1 g del x n minus 1 at x is equals to t plus minus del n minus 1 g del x n minus 1 x is equals to t minus, that will be minus 1 by p0 t, right? And fifth condition is gxt satisfy the boundary conditions. Here we have two boundary conditions and gxt will satisfy these conditions. So by using these properties, we can easily check the options. Option A, symmetric in x and zeta. Yes, gxt is symmetric, so option A is correct. Option B, continuous at x and zeta. Yes, this option is also correct. Option C, we have to check this option. Okay, so according to the property 4, we have del g del x, x is equals to zeta plus minus x is equals to zeta minus, this is equals to minus 1, because in this equation p0t is equals to 1. So if we simplify this according to the given option, then this will be del g del x. From this form, we can easily discard the option C, right? You can check here that here given del g del x, x is equals to xi minus del g del x, x is equals to xi plus, this is equals to minus 1. But we have gotten that x is equals to xi plus minus x is equals to xi minus, this is equals to minus 1. So option C is discarded. Now for option D, this is del g del x, x is equals to xi minus del g del x, x is equals to xi plus, this is equals to 1. Okay, so option D is correct. Now going to the next problem, question number 92, boundary value problem again. For the boundary value problem, y double dash plus lambda y is equals to 0. Y double dash plus lambda y is equals to 0. And the condition are y minus pi equals to y pi, y dash minus pi, this is equals to y dash pi. To each eigenvalue lambda, there corresponds and 4 options are given. Only one eigenfunction, 2 eigenfunctions, 2 linearly independent eigenfunctions, and 2 orthogonal eigenfunctions. Okay, so first of all, here y double dash plus lambda y is equals to 0. So what will be the auxiliary equation? That will be m square plus lambda is equals to 0. Now this lambda, this is our eigenvalue, and this lambda, that will be either 0, positive or negative. So we have 3 cases. In case 1, let lambda is equals to 0. Equals to 0, that means m is equals to 0, 0. So what is the solution? Yx. Yx is equals to c1 plus c2x, right? Now put the boundary condition. If we put the boundary condition y minus pi, here I am writing y minus pi, this is equals to y pi. This implies, so c1 minus c2 pi, this is equals to c1 plus c2 pi. So from here, what we are getting, 2 c2 pi, this is equals to 0. This implies c2, this is equals to 0. Okay, now c2 is equals to 0. Now if we choose the second condition, again you will get that c1 is arbitrary. C1 is arbitrary. Okay, that means from here what we are getting the solutions, yx is equals to c1. This is our solution for lambda is equals to 0. So we are getting an eigenfunctions when the eigenvalue is 0. Okay, now choose the case when lambda, that means eigenvalue, is negative. Okay, so case 2. Case 2 is lambda is negative. Let's say lambda, this is equals to minus mu square, right? Now if lambda is equals to minus mu square, so what will be the auxiliary equation? M square minus mu square, this is equals to 0. So m is equals to plus minus mu. So the general solution yx, this is equals to c1 e to the power mu x plus c2 e to the power minus mu x. Now put the boundary conditions. First boundary condition is y minus pi, this is equals to y pi. From here, what we are getting, c1 e to the power minus mu pi plus c2 e to the power mu pi. This is equals to C1 e to the power mu pi plus C2 e to the power minus mu pi. Okay. Now, if we simplify this from here, or C1 from here, what we are getting, C1. Okay. So C1 plus C2 e to the power 2 mu pi, this is equals to C1 e to the power 2 mu pi plus C2, right? Because we are multiplying this by e to the power mu pi. We are multiplying this first equation by e to the power mu pi. Now, or C1 1 minus e to the power 2 mu pi, this is equals to C2 1 minus e to the power 2 mu pi. Or, okay, let's write it in this form. C1 1 minus e to the power 2 mu pi minus C2 1 minus e to the power 2 mu pi. This is equals to 0, and name it as equation number 1. Now, case 3. Sorry. This is the boundary condition y minus pi equals to y pi. Now, the second boundary condition y dash minus pi equals to y dash pi. Now, if we use this condition by similar method, this will be, because our yx is, this is our yx, here C1 e to the power mu x plus C2 e to the power minus mu x. So what will be y dash x? Y dash x is equals to, this is mu C1 e to the power mu x to the power minus mu x. So we have to put y dash minus mu. So this will be from here mu C1 e to the power minus mu pi minus mu C1 e to the power mu pi. This is equals to mu C1 e to the power mu pi minus mu C2 e to the power minus mu pi, right? Now, or C1 minus C2 e to the power 2 mu pi, this is equals to C1 e to the power 2 mu pi minus C2, right? Because we have discarded the mu from both sides and multiplying both sides by e to the power minus mu pi, e to the power plus mu pi. Or from here, C1 1 minus e to the power 2 mu pi, this is equals to C2 1 minus e to the power 2 mu pi. Or C1 1 minus e to the power 2 mu pi minus C2 1 minus e to the power 2 mu pi. This is equals to 0, and this is equation number 2. Now, from equation 1 and 2, this is our equation 1 and this is our equation 2. From 1 and 2, if we have to find out the value of this arbitrary constant C1 and C2, then we have to find out the coefficient determinant. Okay, so the coefficient determinant is, for equation 1, 1 minus e to the power 2 mu pi, same, 1 minus e to the power 2 mu pi, 1 minus e to the power 2 mu pi. Similarly here, 1 minus e to the power 2 mu pi. Okay, this will be negative. Okay, now this, if we calculate the determinant, this is always non-zero. Now, since this is always non-zero, that means C1, this is equals to C2, this is equals to 0. Why? Because we know that if AX, this is equals to 0, and in this equation, if determinant of A, this is equals to 0, then obviously X, this will be non-zero, right? So for the similar reason, if determinant A, this is non-zero, then that will be 0, right? So by the similar reason, C1 is equals to C2 is equals to 0. Now, if we put the value of C1 and C2 in this equation, then easily we are getting Yx is equals to 0. That means trivial solution. Trivial solutions. And in trivial solutions, we cannot get any eigenvalue. That's why in case 2, that means when lambda is negative, we cannot choose this case because we are not getting any eigenvalue. Okay, so case 2 is not is not appropriate for this problem. Now going to the case 3. Case 3. Case 3 is when lambda that will be greater than 0. Let's say lambda is equals to p square, right? So the auxiliary equation will be m square plus p square is equals to 0. That means m is equals to plus minus ip. So the general solution is yx is equals to c1 px. Now choose the use the boundary conditions. Y minus pi, this is equals to y pi. Okay. Now if we use this, so we are getting c1 cos p pi plus this will be minus c2 sin p pi. This is equals to c1 cos p pi plus c2 sin p pi, right? So from here c1 cos p pi and c1 cos p pi from both sides it is cancelled out. So pi, this is equals to 0. And from here we are getting either c2 equals to 0 or sin p pi is equals to 0. Okay, so we cannot take c2 is equals to 0, because if we choose c2 is equals to 0, then again we will get the trivial solutions, right? So we are choosing sin p pi, this is equals to 0. That means p is equals to n, and n is from natural number. N is from natural number, right? Now the second boundary conditions, y dash minus pi, this is equals to y dash pi. If we use this, then similarly what we have done previous. So just a minute. Here sin p pi, this is equals to 0. That means p is equals to n. So from here what we can say, lambda is equals to n square. Lambda is equals to n square, right? If you use the second boundary conditions, that is y dash, use this condition, again you will see that this type of equation you will get, and either c1 equals to 0 or sin p pi equals to 0, and from here you will again get lambda is equals to n square. So in this case, when lambda is positive, we are getting the solution c1 cos of nx plus c2 sin of nx. The eigenvalue is n square, lambda is equals to n square, and here the eigenfunctions are cos nx, sin nx. Okay, now check the options. Option 1 is only one eigenvalue. No, this is incorrect. 2 eigenfunctions, this is also incorrect, because we have 3 eigenfunctions. For lambda is equals to 0, here this is an eigenfunction, and here for lambda, when lambda is positive, we have gotten 2 eigenfunctions, cos nx and sin nx. So option B, this is also incorrect. Now option C is 2 linearly independent eigenfunctions. Yes, this is correct, because here cos nx and sin nx are linearly independent. So option C is correct. And option D is 2 orthogonal eigenfunctions. Now we have to check these 2 eigenfunctions cos nx and sin nx are orthogonal or not. How we can check it? For this, let's integrate. Integration minus pi sin nx. Okay. Now, if this is equals to 0, then these 2 eigenfunctions will be orthogonal. So yes, this is equals to integration 0 to pi, and this will be 2 cos nx. This is equals to integration 0 to pi 2 cos nx sin nx is equals to sin 2nx dx, and this is equals to minus cos 2nx by 2n, and the limit is from 0 to pi, and this is equals to minus 1 by 2n cos of 2n pi minus cos of 0. Cos of 2 and pi, this is 1, and cos of 0, this is 1. That means 1 minus 1. So we are getting 0. Okay, that means cos nx and sin nx, these two eigenfunctions are orthogonal. Okay, so option 4, two orthogonal eigenfunctions, that will be again correct. So for this problem, option C and D are correct. Going to the next problem, question number 93. Let y1x and y2x form a fundamental set of solutions. Fundamental set of solutions to the differential equation. This equation is given where px and qx are continuous in closed interval AB and x0 is a point in open interval AB. The point is x0 is given from open interval AB, and the two functions px, qx, they are continuous in closed interval AB. Now 4 options are given. The options are saying about the solutions y1x and y2x. In option A, it is saying that y1x and y2x cannot have local maximum. Option B is y1x, y2x cannot have local minimum at the point x0, and x0 is from open interval AB. Option C, y1x cannot have local maximum, y2x cannot have local minimum, and both y1x and y2x cannot vanish at x0 simultaneously. Okay, so this is a problem where the solutions y1x and y2x solutions. Now there are some basic properties of fundamental set of solutions. What are those? For fundamental set of solutions, number 1 is the y1x, if y1x, y2x are continuous. Okay. Number 2, y1x and y2x, that will be linearly independent. And when this is linearly independent, that means Wronskian of y1, y2, that must be non-zero, right? Property 3 is y1, y2 cannot vanish at a fixed point simultaneously. Okay, and property 4 is y1, y2 cannot have local maximum or local minimum. Y1, y2 cannot have local maximum or local minimum at a point, at a fixed point, right? So these are 4 properties of fundamental set of solutions. Number 1 is y1, y2, that will be continuous. Number 2, they are linearly independent, so obviously the Wronskian will be non-zero. Number 3, they cannot vanish at a fixed point simultaneously, and number 4 is they cannot have local maximum as well as local minimum at a fixed point. Now check the options. Both y1x, y2x cannot have a local maximum at x0. Yes, this is correct. Option A is correct. Both y1x, y2x cannot have local minimum. Yes, this is also correct. Option C, y1x cannot have a local maximum at x0. Y2x cannot have local minimum at x0 simultaneously. This is also correct. Okay. Now, option D, both y1x and y2x cannot vanish at x0 simultaneously. This is also correct. That means here all the 4 options are correct. So from 2011 June, in ordinary differential equation section, all these questions are asked, and we have solved all these problems. In the next video, we will solve the ordinary differential equations problems of 2011 December exam. Okay, so stay with us. If you like our video and our content, then please share it with your friends and subscribe our channel. Thank you.